Like the elixir of life, to cure all sickness and make men immortal. These early predecessors of our chemists were called alchemists, and their profession, if we can call it that, was alchemy. Some of the alchemists' procedures were crude, so very little of lasting value has come down to us from their work. Alchemists were often bewildered by the outcomes of their experiments, but such outcomes are easily understood by modern chemists. One of the founders of modern chemistry was... Many discoveries have perpetuated his name, but one of his most famous experiments was conducted with a simple piece of equipment, a large burning glass. With the glass, he focused the heat from the sun's rays on a tube containing some red powder floating on mercury metal. The heat decomposed the red powder. Priestley discovered that a gas had formed as the red powder decomposed. He tested some of the properties of the gas. He was thrilled to find that a glowing ember held in the gas burst into flame and burned with unusual intensity. Priestley had discovered one of the most important gases in nature, but it remained for a Frenchman to offer an acceptation of Priestley's observations. It was Antoine Lavoisier who repeated Priestley's experiments and conducted others. He sealed some tin and air inside a glass flask and measured the total weight. Then he heated the flask containing the tin and air for several hours. A coating of white powder formed on the surface of the tin during the heating. Lavoisier reasoned that the tin must have combined with something out of the air that was in the flask. If so, there should be no change in the total weight. To check his reasoning, he again weighed the flask and found that the total weight had not changed. Lavoisier explained that oxygen, an element from the air, had combined with another element, in this case tin, to form a compound. This combining of an element with oxygen is called oxidation. Only a few elements were known in Lavoisier's time. Today we know of nearly 100. Here in this periodic table, the elements are listed. Each element has a symbol, like O for oxygen to stand for its name. In this table there is much information, such as the relative weights of atoms of the different elements. Teachers and technicians of today have a vast store of chemical information and experience to guide their work. And the young people of today are learning the fundamentals from which may emerge new chemical discoveries tomorrow. To them, each new chemical experiment is a further step in learning to apply chemistry to practical problems. Every chemical compound is the product of a chemical change, and chemical changes are involved in most chemical work. The experiment Priestley and Lavoisier involved such changes. Here is another striking example. The instructor has placed some iodine crystals in a porcelain dish. Next, he adds a piece of another element called phosphorus. When the two elements, iodine and phosphorus, are brought together, a chemical change occurs. The compound phosphorus iodide forms. This compound has characteristics that are different than either the phosphorus or iodine used originally. Problems about the compositions and uses of substances have led to specialization in chemistry. Here are three important fields of specialization that have developed. Inorganic chemistry originally dealt with the chemistry of minerals. Organic chemistry originally referred to the study of plant and animal products. Today, the scope of these fields has broadened. Physical chemistry deals with the rely upon the chemical techniques of synthesis, decomposition, and analysis. Let's look at some applications of chemistry. Synthesis, for example, takes place when two or more elements react to produce a compound, as in the iodine and phosphorus experiment. Synthesis may also take place in nature. Minerals are compounds formed by synthesis. To release the iron in this ore, decomposition, the opposite of synthesis, has to take place. In this smelter, such a chemical decomposition is going on. The metal is being separated from the ore. Chemists have different methods of decomposing a compound. The instructor is demonstrating a method using an electric current.
I have these two tubes filled with an acid solution. It's a common kind called hydrochloric acid. Now, the electrodes in the tubes are connected with a direct current power supply. And when the current is turned on, Phil, would you mind turning that current on, please? The tubes fill up with gas, like that, because the current decomposes or breaks up the acid solution into its two elements, hydrogen on this side and chlorine on this. You can see that each part of the U-tube is filling with gas at the same rate. That's because the hydrochloric acid is made of equal unit parts of hydrogen and chlorine. Its formula HCl, H for hydrogen and Cl for chlorine. Chemists build up and decompose many inorganic substances to produce materials that are more useful. Will you please shut down and test this gas, hydrogen? Now, if I smell the gas, I can tell by the very disagreeable odor that this is chlorine. Hydrogen, on the other hand, is an odorless gas.
Besides color, odor, and taste, there are other tests used in chemical analysis. For example, does this colorless solution contain any dissolved compound of silver? We can find out. If a white solid forms when hydrochloric acid is mixed with the solution, and if the white solid dissolves when an excess of ammonium hydroxide is added, silver is present. There is the white solid. When ammonium hydroxide is added, the solid dissolves. A compound of silver is present. Chemists long ago discovered the silver test. In addition, they have discovered hundreds of other tests, which, because of some color change or the formation of some characteristic solid, tell the chemist which substance he is dealing with. This is qualitative analysis. A chemist may, however, want to measure how much of a substance he has, as well as find out what it contains. An analysis to determine how much is called quantitative analysis. To measure quantity in liquids, graduated containers may be used like this tube called a burette. Some burettes measure as little as a fraction of a drop of liquid. For measuring quantity in solids, different kinds of balances may be used. This is an especially delicate balance. It can measure the pencil lead used to write this dot over the letter I. The weight of any substance is just one characteristic property that may be measured. Every element or compound has many characteristic properties. For example, boiling point is an important property of liquids. In this distillation equipment, one liquid is being separated from another. This is possible because the two liquids do not boil at exactly the same temperature. The one with a lower boiling point is separated from the one with a higher boiling point by this process of distillation. Some compounds, when dissolved in water, have the property of conducting electricity.
Here's an electric lamp. It's all wired and plugged into an outlet right here. Now, the lamp doesn't go on because there's no connection here. When I make a connection, the lamp glows. Here's some pure water in a glass. I put the wires in the water. The lamp doesn't go on. Pure water does not conduct electricity. Now I'll add some table salt. I'll stir it to make a solution out of it. The lamp glows. A table salt solution does conduct electricity.
A solution of an acid will also conduct electricity. Acids have other interesting properties. For example, acids in solution turn blue litmus red. Here, a solution of litmus is added to an acid solution. The color changes immediately. Another group of substances called bases also conducts electricity when dissolved in water. Ordinary household lye is a base. Bases feel slippery to the touch, and they turn red litmus blue. Substances that cause red litmus to turn blue are alkaline. All bases and some salts are alkaline and are called alkalis. All bases contain one part called hydroxide. This part consists of one atom of oxygen and one atom of hydrogen. Since all bases contain at least one part of hydroxide, they're often called hydroxides. Alkalis have applications in industry and in everyday life. Solutions of alkalis are used in the photographic laboratory for developing negatives and prints. So far, we've considered inorganic substances. Another large group of substances consists of organic compounds. All of these contain the element carbon. The first carbon compounds that chemists happened to study were associated with living things, hence the name organic compounds. All living things contain organic compounds. Chemists also produce organic compounds in the laboratory. The preparation here is an organic compound called acetyl salicylic acid. Its common name is aspirin. The formula of any compound tells a chemist which elements are present and in what proportions. The work of some organic chemists is especially concerned with biology. Since their work combines biology and chemistry, they are often called biochemists. Chemists produce many different useful products from the materials available to them. Plastics, for example, are made mostly from organic substances: coal tar, petroleum, and cellulose. Plastics are used in place of metals, wood, and other materials. The industrial organic chemist makes gasoline, synthetic rubber, and other useful products from petroleum. Synthetic fibers lead to improved textiles and increase the variety of our wearing apparel. Synthetic dyes brighten our surroundings. Some of the products of chemical research are used to condition and enrich the soil. Applied organic chemistry produces explosives that do the work of many men in obtaining materials from the earth and achieving other practical purposes. Further industrial uses of atomic energy depend upon learning more about the chemical elements formed as a result of changes in the nuclei of atoms. Chemists are helping discover more and more facts about these radioactive elements. Through such work, the symbol of atomic energy is becoming a symbol of our age. And all the while, research in chemistry continues to point out new horizons and new applications that may prove to be more important than any yet known. By looking backward through the ages at the chemical work of other times, we can appreciate more fully the progress that has been made. Progress made possible by men like Priestley, whose discovery of oxygen led to an understanding of chemical change, and by Lavoisier, who discovered the fundamentals of combustion. Through the relatively few intervening years, chemists have learned how to analyze and synthesize vast numbers of substances. And through discovery of more secrets of the elements and compounds, our chemists of the future will provide products and procedures as yet undreamed of that will still further increase our standard of living. In these ways, we will achieve more of the values that lead to health and happiness.